1 minute ago, on the upper southeast flank of Mount Etna, a fracture almost 100 feet long tore open across the volcano's skin. At first glance, it looks like just another crack on a restless mountain. But when scientists overlaid its position and angle onto ancient maps, something chilling emerged. The new rupture sits exactly where a prehistoric collapse once sent a wall of water across the Mediterranean and erased entire coastlines. This is not a routine scar. It may be the first line in a disaster script the mountain has already used once. At first light, on Etna's southeast slope, the volcano looks almost peaceful. The sky is pale, the last orange of dawn fading over the Ionian Sea, and a thin ribbon of steam drifts from the summit craters. A narrow mountain road cuts across black lava fields and patches of scrub where tourists usually park to take photos of the view. On this particular morning, the first people up the mountain are not hikers but technicians driving slow with hazard lights on, heading toward a cluster of seismic stations and GPS poles that watch the flank day and night. The fracture is obvious only when you are almost on top of it. A jagged line of fresh rock cuts straight across the road and down the slope, almost 30 meters from end to end. The asphalt is torn, one side dropped and twisted, the other lifted just enough that parked vehicles would tilt noticeably. The exposed rock is raw and pale, untouched by dust, rain, or plants. There are no weathered edges, no moss, no signs that this scar has been here for long. It is new, and that is what makes the technicians step out of their trucks, and fall silent. Within hours, police tape and metal barriers seal the road. A temporary exclusion zone is declared around the rupture. Drones are launched from a makeshift staging area, their rotors buzzing as they climb above the slope and trace precise grids over the fracture. From the air, the crack is even more unsettling. It does not zigzag randomly through the lava. It aligns almost perfectly with a known sliding zone that scientists have been watching for years, a corridor where slow-motion creep has been measured in millimeters per year. Now, for the first time, that hidden movement has carved a visible line into the surface. Inside a regional command room far from the mountain, live feeds appear on a wall of screens. One display shows the fracture in high resolution from the drone. Another shows real-time GPS data from the flank. A third scrolls seismic traces from instruments pinned into the rock. Technicians overlay the new fracture on older hazard maps, tracing its position against ancient scarps and mapped landslides. The more they compare, the more a pattern emerges. The new tear is not just on the sliding flank. It sits almost exactly where models of a past catastrophic collapse predicted the main break would have been. Far below, in the towns on the lower slopes and along the coast, life goes on. People drive children to school, open cafes, and watch ferries move across the glittering surface of the sea. Few of them know that a fresh crack has opened above their heads, or that a group of volcanologists are now staring at screens in stunned silence. On paper, this is still just a local structural failure on a restless volcano. But on those screens, it looks like something else entirely. The maps, the drone footage, and the analog traces are all whispering the same question. Could this single scar on Etna's skin be the first visible sign that the entire southeast flank is finally preparing to move? On its own, a single 100-foot fracture on a volcano might sound like a minor surface wound. Etna is famous for cracking, hissing, and spilling lava almost every year. What makes this particular rupture so alarming is where it is, how it is moving, and what it lines up with in the volcano's deep history. First, the location. The new fracture sits on Etna's southeast flank, the very side of the volcano that has been slowly creeping downhill toward the Ionian Sea for decades. GPS stations hammered into the rock have recorded millimeters of motion each year, always in the same seaward direction. Until now, that motion was invisible to the eye, just numbers on graphs and colored arrows on scientific plots. The fresh scar across the road is the first time that hidden drift has carved a clear physical line in the surface. It is the flank announcing that it is no longer just quietly sliding. It is beginning to break. Second, the way it is moving. When teams compare drone images from previous months with today's footage, they see that one side of the fracture has dropped and tilted outward, while the other has lifted slightly. The crack is not simply opening straight down. It is shearing like a book whose cover is sliding away from the spine. Subtle offsets in trees, guardrails, and painted lines on the asphalt show that this is not a random tear, but part of a broader block shift, with the entire southeast slope behaving like a single rigid mass. The fracture is simply the place where the surface could no longer stretch and had to split. The third and most chilling piece is the alignment with the past. Geological teams have spent years studying layers of sand gravel and volcanic debris buried around the Mediterranean. In some coastal cliffs and seabed cores, they have found thick, chaotic layers that contain fragments of Etna's lava mixed with marine sediments deposited all at once by a violent wave. Those deposits point back to a prehistoric flank collapse when a huge piece of the volcano slid into the sea and generated a powerful tsunami that raced across the basin. When scientists run computer models of such a collapse, the simulated main break cuts through almost the exact zone where the new fracture has appeared. That overlap is what turns a local crack into a global concern. It suggests that the structure now failing at the surface may be part of the same failure plane that once allowed a whole sector of Etna to detach. If only a small part of that ancient scar reactivates, the result might be just more cracking and small landslides. But if a much larger segment gives way, the consequences would not stop at the foot of the mountain. A rapid slide of volcanic rock into deep water could shove a wall of sea outward, launching waves that reach not just the Sicilian coast but other countries around the Mediterranean in less than an hour. Add to this the number of people now living in harm's way. Towns and cities have grown on Etna's lower slopes and along the nearby shoreline. Ports, tourist resorts, highways, and power lines all lie on ground that could shake, crack, or flood if the flank fails. Even without a full-scale collapse, a sudden acceleration in sliding could trigger damaging earthquakes, road ruptures, and slope failures that cut communities off from help when they need it most. A crack in rock is easy to measure in centimeters and meters. What is impossible to measure is how close that crack is to becoming the first visible symptom of a much bigger movement. That uncertainty, the sense that the mountain has done something like this before and might be beginning to do it again, is what keeps scientists awake at night. To the scientist watching Etna, the new fracture is not just a dramatic scar. It is a data point in a dense web of instruments that have been tracking the volcano's every breath. Along the southeast flank, steel masts and white dome-shaped antennas mark the locations of GPS stations drilled into the rock. These instruments measure their position with millimeter precision, recording how fast the ground is moving downhill and in which direction. When the fracture opened, those GPS traces didn't just wobble. Several stations on the unstable side jumped in the same direction, confirming that an entire block of the flank had shifted as one. Above the volcano, radar satellites pass overhead along the same tracks week after week. By comparing the phase of their radar echoes, scientists build INSAR maps that show the smallest changes in elevation. On these false color images, stable ground appears in uniform tones while moving areas shimmer with stripes and gradients. In the months leading up to the fracture, the southeast flank had already been glowing with a subtle seaward-leaning gradient. After the crack opened, that pattern sharpened with a distinct band of deformation tracing almost the exact path of the surface rupture. From orbit, the mountain itself seemed to be confirming the story told by the broken road. Closer to the surface, tilt meters and crack meters installed in concrete blocks and shallow boreholes recorded sudden jumps. A tilt sensor that had been drifting slowly registered a rapid change equivalent to the ground tipping by a tiny fraction of a degree, just enough to show that the slope had relaxed in one direction. Crack meters spanning small fissures nearby lengthened by a few millimeters in a matter of hours. Seismometers, meanwhile, picked up a burst of tiny, high-frequency earthquakes, the signature of brittle rock, adjusting as stress was redistributed through the flank. Beneath the surface, gas monitoring stations sample carbon dioxide, sulfur dioxide, and other volcanic gases. A spike in gas flow through vents on the southeast side suggests that fractures at depth have opened pathways for pressurized fluids to escape. That matters because fluids can both weaken rock and lubricate fault zones, making it easier for blocks to slide. Laboratory measurements of the clay-rich gouge that lines the main sliding plane show that its strength drops dramatically when saturated. In simple terms, once enough water or gas seeps into this layer, it can transform from a break into a grease. All of these measurements feed into a volcano observatory where software stitches them into real-time dashboards. Lines on graphs turn colors, shift on maps, and automated systems flag thresholds. When motion or tilt exceeds certain limits, alerts are sent to civil protection agencies. These agencies maintain hazard maps that divide the coast and lower slopes into zones, areas at risk from landslides, areas that could be hit by a tsunami, routes that might be cut off if roads warp or bridges fail. For the tsunami threat, engineers run numerical simulations that model what would happen if a given volume of rock slid into the sea at high speed. These simulations estimate wave heights, arrival times, and the parts of the coastline that would be hardest hit. From this, they design evacuation routes and siren networks, planning how to move coastal populations to higher ground in minutes rather than hours. Drills test these plans in peacetime, revealing bottlenecks where traffic jams form or where communication fails. Yet even the best warning systems have limits. Instruments can tell scientists that the flank is moving faster, that fractures are opening, and that stress is building. They can raise alert levels and trigger evacuations. But they cannot say with certainty whether the next increment of slip will be a few more centimeters of creep or the start of a catastrophic collapse. That gap between data and destiny is where both science and fear live. When scientists play out the worst-case scenario on their computers, the fracture on Etna's southeast flank is just the opening line. The real drama begins when they tell the model to let the entire unstable block move. In the simulation, a huge slice of the volcano's flank, several cubic kilometers of rock and ash, breaks free and accelerates downslope. Gravity does the rest. The mass picks up speed as it grinds over older deposits, breaks apart into boulders and finer debris, and finally plunges into the deep Ionian Sea. The impact pushes an enormous volume of water outward in a single violent shove. Within minutes, a wall of sea 20 meters high is racing towards Sicily's eastern coast. On the lower slopes, towns that see Etna every day as a familiar backdrop suddenly become frontline. Sirens cut through the air. People step out of shops and apartments looking for the source of the sound, trying to decide if this is another drill or something worse. Coastal villages that rely on fishing and tourism have only a sliver of time. In some scenarios, the first waves reach the nearest beaches in less than a quarter of an hour. That is barely enough time to understand the warning, gather family members, and run uphill. Farther away, the threat does not disappear, it spreads. Simulated waves keep their height surprisingly well across the basin, reaching Malta, southern Italy, and parts of Greece in under an hour. Ports, marinas, and low-lying historic districts all lie in zones that colored maps designate in red. Ferries, cruise ships, and cargo vessels could be caught in harbors turned into mazes of churning water and floating debris. Coastal roads that cling to the shoreline might disappear under boiling white water, cutting off escape routes and blocking emergency vehicles. Even without a full-scale collapse, a sudden lurch of the flank would be enough to cause chaos. A smaller slide might send shorter waves into nearby bays while also triggering earthquakes along the mountain's base. Buildings not designed for strong shaking could crack or partially fail. Rockfalls would be likely on steep slopes and in narrow valleys. Key roads could be severed by collapsed bridges or buried under landslides just when they are needed most. Power and communication lines might go down at the same time, leaving communities in the dark literally and figuratively about what is happening beyond their own streets. Civil protection agencies know this, which is why they have spent years drafting evacuation plans, hazard maps, and siren networks. They have identified safe zones on higher ground and mapped the routes that lead there. In some coastal towns, signs already mark tsunami escape paths with arrows pointing uphill. Schools run drills where children practice moving in lines to designated safe areas. Emergency services rehearse traffic control, hospital triage, and the rapid opening of shelters in gyms and community centers. But drills and models have exposed painful weaknesses. Moving tens of thousands of people away from the coast is not just a question of distance, it is a question of time and behavior. In exercises, traffic jams form quickly on narrow roads as cars converge from multiple directions. Some people hesitate going back for belongings or trying to find relatives. Others simply do not hear or trust the warning at first. Simulated timelines show that in many towns, complete evacuation takes hours, not the tens of minutes that a fast-moving wave would allow. Officials are caught in a difficult position. Declare alerts too often and people learn to ignore them. Wait too long and the warning may come after the safest window has already closed. Scientists can say that the risk is elevated, that the flank is moving faster, that fractures like the new one are appearing. They cannot say with certainty, today is the day. Yet the physics of collapse and tsunami leave little room for indecision once the mountain commits. In the end, the consequences of a major flank failure would not be measured only in meters of wave height or kilometers of flooded coastline. They would be measured in lives disrupted or lost, in ports and neighborhoods reshaped in a single afternoon, in the long shadow that such an event would cast over every community, that wakes up each morning under Etna's gaze. The question driving both planners and residents is simple and brutal. If that scenario ever begins to unfold for real, will the systems we have built be fast and strong enough to keep up with the mountain? Inside research institutes and observatories, the fracture on Etna's southeast flank has done more than trigger alarms. It has reopened an old, uncomfortable argument: how close is this volcano to a truly catastrophic failure, and how should the world respond to that possibility? Among volcanologists and geophysicists, one camp looks at the new rupture and sees a warning that was always going to arrive. For years, data have pointed in the same direction: slow, steady movement of the southeast flank toward the sea, repeated measurements of weak, clay-rich layers at depth, episodic pulses of gas and fluid pressure. In this view, the fresh 100-foot tear is not a random crack, but the surface expression of a deep-seated slide plane that has been preparing to move for centuries. These scientists argue that a large collapse is not a question of if but when, and that the apparent match between the fracture's position and the reconstructed failure zone of a prehistoric landslide is far too precise to be coincidence. The more cautious camp interprets the same evidence differently. Volcanoes, they argue, are inherently noisy systems. They crack, bulge, subside, and heal over time scales that are long compared to human lives but short in geological terms. The southeast flank has been shifting for decades without failing catastrophically. From this perspective, the fracture is serious but not necessarily prophetic. It may represent a local adjustment, a way for the volcano to relieve stress in increments rather than in one devastating release. The prehistoric collapse is a reminder of what Etna can do, not a script it is obliged to follow exactly. Beneath this scientific disagreement lies a deeper tension: how to deal with uncertainty when lives and economies are at stake. Models of flank collapse and tsunami allow scientists to explore thousands of scenarios. By adjusting the volume of sliding rock, the speed of failure, and the precise shape of the seafloor, they can generate a wide range of possible outcomes, from localized damage along the Sicilian coast to basin-wide waves affecting multiple countries. But every model rests on assumptions about friction rock strength and fluid pressure that cannot be measured directly at several kilometers depth. Even the best simulations cannot say which scenario the mountain will choose. There is also debate about the role of modern tools like satellite radar and machine learning. Remote sensing has undeniably sharpened the picture. Slow movements that were invisible 30 years ago are now mapped in exquisite detail, and small fractures can be detected within days of forming. Some researchers see this as a revolution, giving humanity a chance to react faster than ever before. Others worry that the sheer volume of data can create an illusion of control. Just because we can see more does not mean we can predict more. The temptation to interpret every wiggle in the graphs as a precursor can lead to false alarms. While ignoring them risks missing the one that matters. Outside scientific circles, the fracture on Etna has become a symbol of a broader dilemma faced by coastal societies around the world. How much risk is acceptable when living next to powerful but beautiful hazards? Towns on the volcano's slopes and along the shore depend on tourism, agriculture, and trade. Strict building codes, frequent drills, and restrictive planning laws all come with economic costs. Local leaders must weigh those costs against probabilities that are hard to explain and harder to feel. For a politician, evacuating tens of thousands of people based on a crack and a cluster of drifting arrows on a map is a very different decision from responding to smoke, ash, and visible lava. Public perception adds another layer of complexity. Some residents have grown up with Etna's spectacles and see the volcano as a familiar neighbor, even a protector. They have heard warnings before and watched crises pass without disaster. Others carry quiet fear and are ready to flee at the first siren. Social media amplifies both extremes. Dramatic footage of the fracture and worst-case tsunami animations spread quickly, sometimes stripped of context. Skeptical voices downplay the risk or accuse authorities of fear-mongering. Alarmed voices accuse them of doing too little. In this noise, the careful conditional language of scientists' words like probable, possible, and uncertain often gets lost. What everyone agrees on is that doing nothing is not an option. Even if the new fracture turns out to be part of a long series of small adjustments rather than the first step toward collapse, it reveals a system under stress. It exposes weaknesses and infrastructure gaps in emergency planning and inequalities in who would be most affected by a major event. The debate is less about whether to prepare and more about how far to go, how soon, and on what evidence. In the end, the fracture forces a set of uncomfortable questions. Should hazard maps and evacuation zones be redrawn now or only after more data confirm a trend? How many false alarms are acceptable to avoid missing one real catastrophe? How do you communicate a risk that may not materialize in any given year but could be devastating if it does? And perhaps most haunting of all, if Etna is quietly moving toward another great collapse, will we recognize the moment when preparation must become action, or will that moment only be obvious in hindsight? On a clear day, it is easy to forget what is hiding in the rocks above the Ionian Sea. Etna rises like a dark island against the sky, its flanks striped with old lava flows and dotted with villages that have adapted to centuries of eruptions. Tourists photograph glowing fountains of lava at night and post them as spectacle. Farmers tend vineyards rooted in volcanic ash. Life continues as if the mountain's only role is to provide fertile soil and dramatic sunsets. The new fracture on the southeast flank tears through that illusion. It is a reminder that Etna is not just a fountain of fire, but a moving structure, a vast body of rock slowly leaning toward the sea. The 100-foot scar across the road is the first visible line in what might someday become a much larger story, a story written in waves, not just in lava. The fact that this fracture lines up so closely with the reconstructed break of an ancient collapse suggests that the volcano remembers paths of failure long after the last tsunami has vanished from human memory. No one can say when or even if a new great collapse will occur. The flank may continue to creep in small steps for decades, cracking roads and walls but never plunging into the sea. Or it may one day cross an invisible threshold when the weak layers at depth and the accumulating mass above them can no longer hold. From that moment, the timeline would compress brutally: minutes for the slide, tens of minutes for waves to reach the nearest shores, less than an hour before other countries feel the impact on their own coasts. Because the physics will not slow down. The only part of this story humans can control is what happens before that moment. Strengthening buildings in at-risk towns, protecting critical roads from landslides, marking and maintaining clear evacuation routes, running realistic drills that expose bottlenecks. These are not dramatic gestures. They are quiet, practical acts of respect for a system we cannot stop but can learn to live with. At the same time, investing in monitoring and research means we can continue to refine our understanding, recognizing small but meaningful changes in the flank's behavior instead of being surprised by them. In the end, the fracture on Etna's southeast slope is both a warning and an invitation. It warns that the mountain's most dangerous movements may be sideways, not upward, and that the sea can be as deadly as fire. And it invites us to take that knowledge seriously, to treat hazard maps and sirens not as background noise, but as tools bought at a high price by those who studied disasters before us. The mountain will choose its own timetable. What we choose between now and then will decide how many stories there are left to tell along these coasts when the next great movement comes.